Welcome, everybody. Our today's seminar is about the C++ library for parallel random number generation called p2rng that I personally developed it. Let's first start with some preliminary concepts that we need throughout this seminar. In the world around us, randomness is everywhere. But is it truly random? To answer that question, we need to know the sources of randomness. Physical randomness is based on Newtonian physics, like tossing a coin and rolling dice. Some like to think physical randomness has better random quality, and that's why it's also known as true randomness. But that doesn't have scientific basis. As a proof, check this quite recent article that found fair coins tend to land on the same side they started. Two problems with physical randomness are they are not high throughput. You have no control over them. If you are interested in this kind of randomness, you can check random.org site. Algorithmic randomness, on the other hand, is based on a computer algorithm. For example, linear congruential generators and Mersenne twister. Some believe they have inferior quality and hence the name pseudo, but I like to refer them as algorithmic. A good thing about them is they are blazing fast. If you are interested in this kind of randomness, don't go anywhere as we are dealing with them in today's seminar. And finally, we have a quantum randomness that is based on quantum physics, like spin of an electron or polarization of photon. Contrary to the previous ones, this one is a real deal. But currently, quantum computers are out of reach for many of us. If you're interested in this kind of randomness, you probably need to wait 5 to 10 years till they become widely available. Let's get back to our interest, which is algorithmic random number generators. Algorithmic random number generators are computer algorithms that can automatically create long runs of numbers with good random properties, but eventually the sequence repeats. The first one developed by von Neumann, but it didn't have a good quality. Then a mathematician named Lemmer made good progress toward this idea by introducing linear congruential generator, or LCGs. Despite being one of early ones, LCGs have some characteristics that make them very suitable for parallel random number generation. Let's review some important attributes of RNGs that we need during this talk. Output bits is the number of bits in the generated number. For example, Lemmer 64 generates 64-bit integers. Period is the smallest number of steps after which the generator starts repeating itself. It's usually expressed in power of 2. And that makes it to be confused with output bits sometimes. For example, PCG32 is a 32-bit generator with 64 bits of state or period. State is an initial value that determines the sequence of random numbers generated by the algorithm. And finally, footprint is size of the internal state in bytes. For example, Lemmer 64's footprint is 16 bytes. As a simple test of random number generator quality, you can look at its randomgrams. There shouldn't be any recognizable pattern in the white noise like the one you can see on the right here. But if you see something like this one, then something is wrong with your generator. And if you get this, then something spooky is going on in your generator. But seriously, if you're interested in this kind of party tricks for Halloween, some generators like PCG can do that for you. There are some batteries of tests for RNGs, but I'm not gonna talk a lot about it. First one was Die Hard, and then Die Harder, followed by test U01, which is considered as a gold standard. It includes 3 subsets: small crush, crush, and big crush. To be a good random number generator, it is not sufficient to just pass big crush. But if it can't even pass big crush, there is a problem with it. On the right, you can see Lemmer 64 source code, which is super simple and super fast generator that passes big crush. The reason it's included here is that it perfectly shows the 2 parts of a generator: the state transition function and the output function. And last but not least, reproducibility versus playing fair. An algorithmic random number generator must be reproducible. That's the whole point of having them. It means using the same seed and distribution, you should get the same sequence of numbers every time. But it's more in a serial context. Playing fair is something with parallel Monte Carlo simulations. In parallel Monte Carlo simulations, playing fair means the outcome is strictly independent of the underlying hardware. That means you should get the same sequence regardless of the number of parallel threads. Both reproducibility and playing fair are mandatory for debugging and unit tests. Now let's change our gear and see how we can generate random numbers in C++. Before C++11, there were only 2 functions for random number generation: rand to seed the random number generator, and rand commonly based on LCG or linear congruential generator to generate the next random number. And the common practice was to use modulus operator to bring them into a range. Since C++11, random library became more sophisticated and provided multiple engines and many well-known distributions adopted from Boost Random library. Engines act as source of randomness to create random unsigned values, which are uniformly distributed between a predefined minimum and maximum. Distributions, on the other side, transform those values into random numbers. There is a great talk by my colleague Paul Perini that goes into nitty-gritty details of using C++11's engines and distributions. You can check it by going to this link. Let's first see how we can use an engine and a distribution to come up with a simple serial program. Here's our first attempt with a for loop. That's really straightforward. We just need to include the headers. And as you can see here, we just choose a number as a seed. And we start with 100 random numbers where we want to put them in a vector of integers. And we use the Mersenne twister, one of the very common engines as our generator or engine. And we use uniform integer distribution in the range 10 and 100 for producing our numbers. Here is the new C++11 for loop using the references of A. And we use the distribution and engine to initiate the values. If you are interested, this is the old way of the for loop. And finally, we have our a for loop for putting the output on the terminal. And here is the output: 100 random numbers between 1 and 100. Those with eagle eyes may notice something in the output. I intentionally chose the spacing in the output by setting the width to 3 to prove a point. The distributions in C++ random library accept closed ranges or intervals. It means 10 and 100 are both included. Here's our second version with STL's generate algorithm and also Lambda. Let's highlight the changes. The only thing that you need is to add the algorithm header here and then calling the generate algorithm, which starts with iterators for the begin and end of the vector. And we use a lambda. And that's especially important here. I marked the ampersand with red here for a reason that we need to pass engines as a reference here. That's especially important because, for example, for some engines like Mersenne Twister that has a big state, it makes them it's better because it takes a long time to initiate the engine. For other engines, it's maybe not like that, but for Mersenne Twister, it's for example like this. We can also use generate n, which is another algorithm, pretty similar. And here are the only changes. We just changed the name to generate n and also pass number of n rather than the end of the vector here. But the lambda is the same here. And we get the same results as well. But there is yet another way with a standard std bind function. Here are the changes. You only need to include header functional here, and then replace that call, replace the lambda with a std bind, which binds the distribution and also the engine. But for passing the engine as a reference, we need to use another STL function called stdref, also defined in functional, to pass the reference. And we get the same numbers. So this is our initial serial version of our program. Now let's try to make it parallel here. C++17 supports parallel algorithms using execution policies. So let's use it to make it parallel. Here are the changes. We only need to include the execution header, which defines the parallel execution policy, and then add another, our parameter here and passing this, execution policy as the first, argument to generate it. That's it. But something that we need to notice here is that C++11 random engines are not thread safe. So in our first attempt, we pass a copy of the engine rather than reference to see what happens. You can see that the output is not quite what we expected, but if you think about it, that was obvious because when you send a copy of the engine, for each thread, we have a new engine initiated with the same number of, the same seed, and it starts with 35, and it's going to be the same for all the numbers like this. So we can't do it like this. But for the second attempt, let's try to pass the reference of the engine and see what happens. It's not thread safe, but let's see what we get. So the only change that we do here is changing the passing engine by reference. And we get the same results as serial version. That's interesting. Let's try again. Again, we get the same results. So it seems like without much effort, we nailed it, right? Not quite. Going with higher number of random numbers, for example, 10K, rather than 100, will turn the table and we get similar but different sequence of numbers on each run. But that's not the actual problem. The real problem is that it's even slower than serial version. You can check it simply by increasing n to 10 million and commenting out the output, and then using the time commands in bash to run both versions. If you do that, you can see clearly that parallel version is, here takes more than 1 minute, but this one is less than 1 minute. So clearly the serial version is faster than parallel. And here is a more accurate performance analysis using Google benchmark on AMD EPYC CPU with 128 cores. We start with 1 million and then increase it to 16 million. This is a common practice. And during this time, bandwidth should be stay the same. You get the timing here. If we focus on benchmarks with 16 million integers, we can find that parallel version is more than 3 times slower than the serial version. So the verdict is that it's easy to do and implement, but it has a terrible performance. There is a possible correlations in subsequences, and it cannot play fair. In this slide, you can see 4 proven techniques to introduce parallelism into algorithmic random number generation. These are general techniques that can be used equally well in shared memory, distributed memory, and heterogeneous setups. Let's start with random seeding. In random seeding, all parallel threads use the same engine, but a different random seed. So here are all the changes that we need. One thing that we should notice is that, unfortunately, there is no way to have thread numbers in C++11. That's really odd. You can easily do that, for example, in OpenMP or MPI, but it's not, you can't do it in C++11. So a workaround this is that we can get an ID for the thread, which is, defining the header thread. We can use that one to get an arbitrary number or ID for the thread, and then using the hash feature or feature of the C++11, convert it to a hash, which can be different for each thread, and then pass it as the seed for the engine. But another thing that we need here is thread local keyword, C++ keyword, to make the thread make a local copy of this engine there. By doing that, we get our results. But as you can see, for each run, we get different sequence of numbers. No matter what seed we provide, there are different numbers. But the good thing is that it has a good performance, better scaling at least. You can see the same benchmarks here on EPYC CPU. And focusing on benchmarks with 16 million integers shows parallel version is about 50 times faster than the serial version. So the good thing is that it has obviously has a good scaling, but there is possible correlations in subsequences, overlapping of subsequences, and also it cannot play fair. Let's go to the second technique, which is parametrization. In parametrization, all parallel threads use the same type of generator, but with different parameters for each thread. For example, LCG generators, for example, Lemmer that I showed you, support an additive constant for switching to another stream, which is called multiple streams. To do that here, we need to use a generator or an engine that supports this feature. So that's why I added this header, which uses the PCG random generators. And we have to use the same technique here because obviously C++ doesn't provide us with the thread number. We use the hash here again, but we changed the engine from Mersenne twister to PCG32 and pass this one as the second argument to R, which is supported by PCG, which starts a new stream. So each thread starts with a new stream of sequences. So running that, we get another result, and like the previous method or random setting, we get different results on each run. And if you check the results, the performance is more or less like the previous method, but we still have the same problems. Fortunately, overlapping is less possible, but engine must support multiple streams, and there is also possible correlations between the streams depending of the implementation of the engine and the streams, and it cannot play fair. So let's go to the next two techniques. First, let's start with leapfrog. The leapfrog method distributes a sequence of random numbers over parallel threads as illustrated in this diagram. It requires an efficient way of jumping ahead in the sequence, which is supported, for example, by LCG generators. As you can see here, each thread put the next value in the sequence, so it's completely possible for the threads to access cache line at the same time. So it's prone to false sharing. If you want to generate the numbers on ad hoc basis, it doesn't happen. But if you want to store numbers like the way we do in an STL vector, then false sharing will be there. So unfortunately, because we need to have a different generate algorithm, we can't implement it like the way we did for the first two methods. But here are the good thing is that there is no overlapping or no correlations, and it can play fair. But the period is shortened by a factor of number of threads, which is something important when your engine has a small period. It's prone to false sharing, as we said. Jump ahead feature must be supported by the engine. And as I said, we need a modified version of generate algorithm. If we go with the last method or technique, which is block splitting, it's more or less the same. Block splitting splits the sequence of a sequential RNG into consecutive blocks as shown in this diagram. But because the blocks are spaced enough, there no false sharing happens because each thread's responsible for different blocks. And like leapfrog, it requires an efficient way of jumping ahead in the sequence, which is supported by some engines like LCG generators. Pros are more or less the same, no overlapping, no correlations, and can play fair. But fortunately, false sharing not happening here. The period is shortened again by factor of number of threads. We need jump ahead feature, and also we need a modified version of generator. Overall, block splitting seems like a good match for our purpose, but there is a missing ingredient. We need a custom-made version of generate algorithm. And that's where p2rng library comes into play. But before explaining what p2rng is, let's see what are our options. There are other ecosystems and libraries that help you generate random numbers in parallel. CUDA, ROCm, and OneAPI all provide their own parallel random number libraries, QRAND, ROCRAND, and OneMK. But their interface is not compatible with STL and also each other, plus they don't play fair. On the library side, SPRNG is one of the first parallel random number generation libraries, but it only supports distributed memory architecture or MPI, and it's not updated for a while. But TRNG4 is by far the most complete implementation of parallel random number generation library that is also compatible with C++11. While 3RNG4 provides all the necessary classes and methods and tools, it doesn't provide any implementation of parallel algorithms. And depending on the problem, you should do it yourself. And finally, let's see what is p2rng. p2rng is a modern header-only C++ library for parallel algorithmic random number generation. Let's check the features here. It's multi-platform. You can use it under Linux, Mac OS, Windows. It supports 4 target APIs: OpenMP, CUDA, OneAPI, ROCm, and it provides parallel versions of STL algorithm, generate and generate-n, which is based on block splitting techniques that we already mentioned. The good thing about it is that it plays fair on all supported platforms. No matter you are on CUDA, OneAPI, GPU, CPU, you always get the same sequence of random numbers using the same seed and distribution. The only included engine for now is p2rng family, but maybe other engines added later. And it includes 32 distributions provided by p2rng4 library, which are already compatible with C++11. It also supports CMake for building and auto configuration. There are 3 necessary and sufficient conditions for playing fair. Here, first, algorithm must support it. You should either use leapfrog or block splitting technique. The engine must support it by providing an efficient jump ahead method. For example, discard function in C++11 standard. For example, discard is in C++11 standard, but Mersenne Twister, because it doesn't support that, doesn't provide any discard function. And finally, even the distribution must support it by not discarding any values generated by the engine. It's common for some C++ distributions, C++11 distributions, that they discard some of the values. And if that happens, you don't get the same sequence. p2rng fulfills all of them by using block splitting technique as an algorithm and using p2rng family, which provide discard, and this discard has a complexity, O complexity of log n, which is much, much better than n, for example. And it uses the distribution by p2rng4. To my best knowledge, the only library that provides such distributions that are also compatible with C++11 standard is p2rng4. These are designed in a way that they don't discard any values. So here are the necessary changes to convert our serial STL code to parallel p2rng. As you can see, the changes are minimal. You don't need algorithm or functional headers anymore, and you should add p2rng header instead. The only supported engine for now is p2rng. So you can use, for example, p2rng32 or p2rng64 here for the engine. And you have to change the std namespace to p2rng namespace. There are 2 things that should be noted here. p2rng only supports bind method and not any other ways like lambdas or functors that we showed. So you can't use lambdas here. You should stick to p2rng bind method here. And p2rng bind doesn't accept reference to distribution because it needs to send separate copies of engine for different threads. So you shouldn't use std ref here. That's all the changes. And for the bind, you should use p2rng as well as a namespace rather than std. Once you do that, your code is, parallel, becomes parallel and also plays fair. Here is the, benchmarks, again, on EPIC CPU with 128 cores. To be comparable, all the benchmarks here are changed to use PCG32 rather than Mersenne Twister. And if we, again, focusing on benchmarks with 60 million integers, we can see that p2rng is more than 72 times faster than the serial version here. And here are the necessary changes to convert our OpenMP code to CUDA or ROCm. You need to add the header for the Trust device vector. Trust is a library in both ROCm and CUDA ecosystem. You need just add this header. And if you don't use STD vectors, you can omit this line as well and change the STD vector to Trust device vector instead. And the last change is to use the CUDA namespace for the p2rng generate end function. And that's it. And the whole code is going to run on GPUs. For the ROCm, the only change is changing CUDA to ROCm. And that's it. And finally, this is the changes that you can do to convert the OpenMP code to one API. Here again, you need the header, these two headers, one for DPL iterators and one for SQL. And you change the STD vector to SQL buffer and change the namespace for the p2rng generate to one API. But there is one more thing. You need to use SQL host accessor to access the vector on host for printing the results. For ROCm and CUDA in Trust, this happens automatically, but for SQL, you should specifically mention that. Once you do that, you can have the results. Now, let's change the gear to the live session and see how we can use p2rng in our programs or in our projects. Here is the link to the GitHub repository. You can use this QR code instead as well. Let me now switch to my terminal here. Here I'm on Narwhal, and let me first show you the GitHub repository here. You can see the whole repository has all the information in the first page to give you a head start. It also has the GitHub actions, which automatically tries to build and test under 3 operating systems, Linux, Mac OS, and Windows. As you can see that it's all passing. It has an MIT license as well, so you can use it easily in your projects. If you want to start using it, you need to first build it on your system. Let me go building from source here. It relies on CMake. Unit test and Google benchmark are used for the benchmarks, but these are optional. You don't need them. But on the Alliance clusters, because Google benchmark and Cache2 are already there, you can load them. And you need a recent version of CMake 3.21, so you should load CMake as well. So all I need to do is just copy this line and put it here. But let me first go to Scratch here and then module load this. And I just need to git clone this here. All the instructions are like the one in the main, repository, but I just try to type them now here. Here, we can use CMake, and with this to build it in a out of source folder called build. It automatically tries to build the release version if you don't specify anything. And the default version is for OpenMP. But no matter what you want, when you install it, you can switch to other platforms if you want. Once it's configured, you can use this command to build. And passing -j to use multiprocessor build. So the only thing that happens here is unit test and benchmarks. If you want to run the unit test, you just go to build and run ctest. Okay, if I use perf, now you can use the benchmarks. But for the benchmarks, I shouldn't run it on the login node. I should, use slog to have a dedicated node with the number of, CPUs that I want. I'll show you later this. But the thing is that you can build it for different platforms as well. But one problem here is that if you want to install it, because it's you need the, you can use it. You can do CMake install build to do that. But by default, it's going to install it in the system directories, which you don't have permission for that on clusters. So one easy way to do that is to install it in your home directory. If you want, you can do it from the beginning. Let me show you like this. If I remove the build, I can try again this time by providing CMake install prefix to be my home to be my home. And by this, when you try to install it, it tries to install it in your home directory. And oh, sorry, I am in the build folder. First, let me remove the previous one, and then try to build it again. There is also an option that you can just switch the CMake install prefix in the install phase. But I try to show you from the beginning. You can do this way to tell CMake that we want to install all of them in the our home directory. And after that, using the same command, I have it. Let's have it here. We can build it. And then if I use CMake install build, it will install it in my home directory. You can see that. There is also option to install it in home.local, which also works, because the good thing about the p2rng is that it uses the CMake for configuration. So when you use a CMake script to do that, it tries to find the configuration from the places that is installed. For your projects, the best way to include p2rng is to use the CMake. And this is the minimal thing that you should add to your CMake. But if you want a complete example, if you check the example folder here, you can see a complete example that has a CMake script ready for you. And, something similar, the one that I showed you. And it tries to compile it for different platforms. So let me do that for you here to see how it happens here. So for example, if I go here to example folder, this is the complete example. There is a CMake list text, there's a README, the same README, and 4 different files. One CUDA version, one API, OpenMP, and Rock'n. The CMake scripts is designed like this. Let me show you in the source here. It tries to find CUDA. If it finds it, it tries to build the CUDA version. If not, it just doesn't. And the same for HIP and one API. But one API and OpenMP versions are mutually exclusive. It means that if it finds one API, then only build one API version. And if it doesn't, it builds the OpenMP version. So here, for example, let's see. If I do CMake build, dash s dot dash b build. I didn't load CUDA. Usually it shouldn't find it, but sometimes it does. Let's see. So we don't have ROCm on clusters. Oh, so yeah, you can see that it couldn't find CUDA and HIP compiler and one API. So the only version that it's gonna build is one OpenMP. So if I do CMake build dash J, it only makes the OpenMP version. But let's say that I want to build CUDA version as well. The only thing that I need is module load CUDA. And if I try to build again, usually in perfect situation, it should do that. But maybe, there is, the thing is that maybe you need to run the build again. So you should configure it again, probably. But so if I do the configuration again, this time it should find CUDA as well. It takes more because, so OpenMP is already found. I don't see. Okay, now it found CUDA. Yes, we have on CUDA compiler. And now if we do the same build command, it should build both CUDA and OpenMP version. So if I run the OpenMP version, I get this result, and I expect to get the same results with CUDA. But I can't do that here, obviously, because we are on login node, and login nodes don't have GPUs. You can see that if I run it, it complains. So if I want to run the CUDA version, okay, I should use the salloc command. Let me use cc debug as my account. And I request for 5 minutes. The only thing that I need is to mention GPUs per node equal to 1 to go to a GPU node. And if I now use run the CUDA version, I should get exactly Same results. You can see it here. If you are interested to run some of the benchmarks, I have some benchmarks also. If you, there are some, if you go to the per folder, the repository, there is some results here, but you can also run it yourselves. You can see the results for our fastest GPUs, A100 CUDA, and also we have a machine with MI210 on SharkNet, which is not publicly available. But if you want the results of the benchmarks, you can find them here as well for the library. But these one are for float and double. And you can see that it's quite good, especially for if you check the results for MI 2010, 210, you can see that it's not completely filled the bandwidth, which is like this, but it's quite good. And for 16 million runs, it's takes less than a second. And that's all the things that I wanted to show you by now. So thank you very much for your patience. If you have any questions, I'm ready to answer them. Thank you.